Hello everyone! In this video we will continue to examine topic 4.5 standing waves, and in particular we will continue to examine standing wave patterns in pipes. In the last video we introduced the idea of standing wave representation in a pipe, or standing waves in pipes. Notice that we are going in general, when analyzing both half-open pipes and open pipes, to want to use the transverse representation. Why? More or less because it's easier to draw. We want to remember what it means in terms of the longitudinal wave that's actually being created in the pipe. But the transverse representation will allow us quickly to move to the equations that govern the relationships between the wavelength, the frequency, and the length of the pipe. So, for a half-open pipe, as we discussed, there is a quarter wavelength seen, and therefore lambda over 4 equals L implies that the fundamental frequency is equal to V over lambda, which is equal to V divided by 4L. Okay? But now consider what happens when you move to the next harmonic. The important thing to recognize is that for a half-open pipe, you have a node at one end and an antinode at the other. You always need to have a node at the fixed end and an antinode at the unfixed end. As a result, the next pattern that fits in our pipe has one extra antinode and one extra node. So we increment both the antinodes and the nodes. Let's take a look at what this means. Well, if I draw a node right here and an antinode right here, then I'm going to need to have an antinode here and a node here. Remember that an antinode means that in the longitudinal wave, okay, you get maximum displacement at those points and zero displacement at the nodes. Now take a look at how the wavelength relates to the length of the pipe. This diagram shows us that we get almost a full wavelength in the pipe. And in fact, we get exactly 3/4 of a wavelength. So 3/4 lambda equals L means that the fundamental frequency, the frequency of this particular harmonic is equal to V over lambda, which is equal to V over 4L divided by 3 because of our relationship here. This means that the frequency of this harmonic is 3 times that fundamental frequency. Notice this is in contrast to our strings, where the first harmonic that we derived was 2 times that fundamental frequency. This is no accident. We call this structure and this frequency the third harmonic because it is 3 times the fundamental frequency. And for a half-open pipe, there is no second harmonic. You might extend this pattern forward. You might think it might extend, and you'd be right. So the next harmonic we'll call the fifth harmonic, and we would expect it to have 5 times the fundamental frequency. Let's show that that's true. So we draw our diagram. That's always the first step. Notice that our diagram has an extra antinode compared to the one above it, and an extra node compared to the one above it. And we see that there is a full wavelength and an extra quarter wavelength that fit in the half-open pipe. So 5/4 lambda fit in L. Therefore, the frequency is V over 4L divided by 5, and therefore 5 times the fundamental frequency. We can summarize this pattern in a series of equations below, although my strong recommendation is not to memorize these equations, which are not given, but instead to remember how to draw the diagrams and to remember how to get the equations from the diagrams. This you should practice. Nevertheless, if we can summarize these equations by observing that for any n, we can get the frequency of a particular harmonic by incrementing n. The fundamental frequency is just 0 plus 1 times f naught. And then for n equals 1, notice that we plug n equals 1 in here. We get 3 times f0 is equal to f sub 3. So the third harmonic frequency is equal to 3 times the fundamental frequency, and likewise for our wavelength equation. The last remaining topic we're going to cover in standing waves is to follow up on open pipes. So, where half open pipes had one fixed boundary and one unfixed boundary, open pipes have two unfixed boundaries. And we draw our first harmonic here, and we observe that we have an antinode on both ends because they're open, and a node right in the middle. One thing to remember, it always looks a little silly to draw these diagrams because it looks like it's just two lines. But remember that you're looking at sort of a cross section of a three-dimensional pipe. So this is a pipe open on both ends. Um, so we take a look at this diagram and we observe we go from one side fully to the other, but no more, which means we can see exactly one wavelength divided by 2, or half a wavelength. If lambda over 2 equals L and the frequency is V over lambda, then the fundamental frequency is V over 2 lambda. If this looks familiar, that's because it is. This is exactly the way a string with two fixed boundaries works. And in fact, two fixed and two unfixed boundaries, although the diagrams look different, the frequencies and therefore the harmonics follow the same pattern. So let's prove that for ourselves. Let's draw the next open pipe. Note we're going to increment the number of nodes and antinodes. So we go up by 1 in both. We have 3 antinodes here and 2 nodes. And as a result, we see a full wavelength. Note that this is basically one peak to another peak. Therefore, lambda equals L. And if lambda equals L, then the frequency is equal to 2 times the fundamental frequency. Just as one might have predicted, the second harmonic occurs at double the frequency of the fundamental. And this is exactly the same pattern as in the case of strings. You can prove to yourself that the pattern continues to hold for the third harmonic following these relationships. Notice that this set of equations then is identical to the set of equations for the string with two fixed ends. Again, strong recommendation is not to memorize the equations, but instead to draw out the diagrams every time. There are several example problems over the next 2 slides that you should absolutely take a look at and work your way through.